So in 13.1, now we've left vector valued functions. We've are more dealing with rectangular coordinates, and then obviously we'll get to polar and stuff later on. But important to make sure we're all on the same page here. When we had a function f of x, this was a function in terms of one variable, right? Mainly x. Sometimes we called f of x y. Okay. So we may see two variables, but really we're talking mostly about the input. So if we have one input variable, we say it's a function in one variable, even though we may call it y equals 4x squared. Okay. So y is the same as f of x, which is 4x squared minus 2. Okay. Now, in this class, you're going to start seeing things like z equals. And typically, we'll define z in terms of two input variables, two dependent variables, x and y. So these are now considered the dependent variables. Or, I'm sorry, independent variables. And z is the independent, or the dependent. Jeez. Z depends on x and y. You've already seen functions like these before. You've probably never wrote a formula like area equals 1/2 base times height in terms of two variables, but that's actually what that is. It's a formula in terms of two variables, b and h. Okay, so you've been dealing with multivariable functions here and there, you just never really called it that. Now, if we want to have three independent variables, the book typically uses w as the new dependent, and you will occasionally see a function in three variables. So now x, y, and z would be your inputs, and w will be your output. Okay? Now, if we look just at the typical, the domain of f of x, y comes from the restrictions on x and y. Okay, and that will determine the domain of that function. Okay, so let's try a couple of examples. Let's say we wanted to find the domain of f of xy equals natural log of xy. How could we find the domain for that function? Neither x or y could equal 0. That's true. Can we have a negative in here? So
X and Y must both be greater than 0.
the product, right? So we have this restriction. Can we sketch where that might be? So where's the product going to be greater than 0? First and third quadrant, good. So as long as we're in the first and third quadrant, we have a function here. So let's say the domain is all ordered pairs x and y in quadrants 1 or 3. So as long as this product is positive, we're good. Okay, what about if we have f of x, y, z, and let's say that's equal to x over the square root of 9 minus x squared minus y squared minus z squared. What can we say right away? Why not equal to? Okay, so we don't want 0 in the denominator. So that means that we can only have positives in the square root, right? So, good. This needs to be positive. And then if we clean that up a little bit, we can say 9 is greater than x squared plus y squared plus z squared. So basically, this would be a good way to say the domain if we describe it in words. What shape is this? Sphere's radius is 3. Now where are all the points that we want to include? Is it outside or inside the sphere? If it's less than 9, it means the radius has to be smaller than 3, right? So the domain would be all x, y, and z inside a sphere, not on, but inside a sphere of radius 3 centered at the origin. Okay, so that's kind of the background. Now I am pretty confident that if I asked you for that same function we just had to find f of 2, 1, 1, that we could all handle that. Why don't you go ahead and take a few seconds to work that through. No, just find f of 2, 1, 1. Using the last function, so using the same. So how do we do such a complicated problem? You just plug it in, yes, okay. Just making sure we can all do that. So we get 2 over the square root of 9 minus 4 minus 1 minus 1. So we should all get 2 over root 3. So evaluating functions should be pretty straightforward. Finding the domains, if you can find the domain of just one thing, you should be able to handle finding the domain with more than one variable. Okay? Now, in addition to evaluating and finding some basic domains, yes?
Wait, so these, like the ones with X, Y, and Z,
These are actually in 4 dimensions.
no, the ones with like just X, Y, and Z are Greek, right? Like Z
Well, it depends on how we write it. If we say z equals f of x, y, that's 3-dimensional.
But this is 4.
This is 4-dimensional,
Are
yes.
we supposed to graph?
We're not going to graph it because we can't.
How, but like, what is the significance?
Wait, did you watch that video that we watched
One video, one
Do you guys remember the one about the dimensions? It was like a circle.
I read Flatland.
Yeah, that. We
I
watched
read
it.
it.
We watched
I-
the animated version.
After you, there was.
Oh, yes.
Can we watch
Flatland.
that?
Maybe we can. Flatland.
It was so awesome.
Anyway, here's what you need to know. Yes, there are common interpretations that in our little world we cannot conceive and visualize, but time could be considered a 4th dimension.
True.
It was
Okay.
actually a circle.
But it really doesn't matter because the mathematics, when you extend to 4, 5, 6, and 7 dimensions, it's all the same.
There's 11.
So you could even say that there are more. Okay.
M theory says there's 11
Different theories state different things.
My theory.
There's 11 what?
dimensions.
Layers on
There's 3 of like that way, that way, that way.
it.
And there's 1 of time, and the rest are like curled up really, really tiny. We can't see them.
I gotta see time.
Yeah, I was just gonna
You
say.
know what?
If you have a way of graphing that, no.
I mean, you would need to use like a hypercube or something.
Okay. So now we're going to put some things together from before. Like you should still be able to sketch some basic graphs like you did in chapter 11. So to help you, don't get confused with the notation. This is the same as z equals, right? So how would that graph look like?
Oh, so it's like a z squared equals that thing, and so they're all squared.
Sure. So if we think about it as z squared equals 4 minus x squared minus y squared, rearrange some stuff, right?
Are those one of the hyperboloids? Or not hyperboloids now?
It's like a, what is it, the ellipse? It's a sphere.
Elliptic. It's just an ellipsoid, but it's really not an ellipsoid because it's the top half, and it's really a sphere, right? Because all the radii are the same. So this tells us that z has to be greater or equal to 0, right? Because we have the square root of all that stuff. So even though we know that if we move some stuff around and manipulate algebraically that we get a sphere, we only want the top half. So if we had to sketch it, then you would just sketch, bless you, something like this. Okay?
So there was only the restriction because it was originally under the square root.
That is correct.
If it was like a plus or minus, it would be the whole thing.
So if we had plus or minus, then yes, it would be the whole thing. But now then we would argue, well then it wouldn't be a function to begin with.
Yeah.
We're going to deal with functions only, so
That's,
okay. One more.
are we just like doing examples now? Or?
Another, just to review some of these shapes, because again, these are things that are going to come up frequently. And then we'll talk about some more new stuff that we haven't dealt with yet.
Are we gonna do partials?
That's coming up soon, yes. Okay, so what would this shape be?
Elliptic paraboloid.
A
No,
thing.
It's just half of the sphere.
It's not a sphere.
It's not a sphere.
I'm sorry.
Oh, z equals x squared plus y squared.
Isn't the
So-
elliptic paraboloid?
It's one of the things we learned.
If z is not its own.
Oh,
Because the z
It's
is
one of the
square.
things we studied. Yes,
And
yes it
since
is.
we're adding it. It's, well, we have to know. It is.
Yeah, you do have
but
to
it is
know.
also half the sphere.
Centered at the
That
origin.
one happens.
Its vertex is at the origin.
Vertex.
Is that a
Elliptic
parabola?
cone,
A parabola.
It is a paraboloid,
Yeah, I
yes.
guess.
but it's also.
It's not a sphere.
It's
Half
an
a sphere.
elliptic
No, because this
paraboloid,
continues indefinitely.
not a
Oh.
hyperbolic
Then why don't we-
It's not like a sphere cut in half and flipped upside down. Remember, this extends indefinitely, so.
An inverted sphere, but only half of an inverted sphere.
If you take
So, yeah, you should pretty much know those basic shapes. You'll see them a lot in this unit and in the next one and in the next one.
So this
And
like
then
the
never
9
again
basic
in our lives.
functions.
Well, you might see them depending on what other stuff you take. Okay, so then it leaves us with basically two more things. What we call level curves, which If we collect all the level curves, will give us what we call a contour plot, which you're probably familiar with. And then, of course, a level surface, which is the extension of a level curve into 4 dimensions.
But
So let's start with level curves. So if I have a sketch of some surface, so here's a happy surface in 3 dimensions. Let's say it's z equals f of x, y. And I decide to cut through horizontally. Like slice this surface. Okay, then within we might get something that looks like this. Okay, and this blue curve, that's what we call a level curve. Okay, so imagine taking any surface, slicing it, and then the path, the edge, that creates what we call a level curve. Okay, and now we can certainly, let me change colors here. Yes. And we can certainly take this level curve and then plop it on down to the xy plane. So pretend that this orange and blue one are the same. I know they're not, but. And if I'm not going to do it, but if I took another slice, maybe more in the positive z direction, we would get something similar but a little larger. Does that make sense? And if I put that on the xy plane, maybe I get a different level curve. Okay? So this orange set on the xy plane, this is the set of level curves. And together, this is what we call a contour plot. Okay? Now each level curve, even though we're going to put it on a 2-dimensional plane, each level curve is going to correspond to a z-value. Okay, so this green plane, maybe this was z equals 2, let's say. So then this first level curve here corresponds to when z equals 2. And if I were to maybe go up 1 unit, and that's how I got this other level curve, then this curve corresponds to the z coordinate of 3. Okay, so the best interpretation possible would be, here's a contour plot. We have a whole bunch of level curves on the contour plot, and each particular curve represents a height or a depth, if that makes sense, because that's how we interpret z. Yes?
You're placing the contour plot at the bottom of the figure?
Yes, so actually when we draw a contour plot, we'll just use a normal xy plane,
Okay.
and then that's how we're going to draw them, yeah. I'm just explaining the geometry of where this is going to come from visually. Yes?
so it's not the bottom of the curve, it's just like on the plane.
Right. We're projecting, like we take a slice, we take that, translate it on down to the xy plane. Take another slice, take the path.
So like let's say the curve doesn't sit exactly on the XY plane, just put the contour plot.
We're going to put them on the xy plane anyway, because we would label, like for instance, this first curve on the inside, if you were walking anywhere on this first curve, you would be at a height of 2 no matter what you did, right? But as soon as you start to deviate from that path, and let's say you start to go outward, just by looking at the contour plot, you know that now you're not going to be at a height of 2, but you're going to start to climb up a little bit. Okay? Yes? That's exactly where we see these, yes, exactly. that comes into play too, so you can use gradients to interpret, depending on the contour plot, you can get an idea of how steep the gradient would be. Yes, and we'll do that, just not quite yet. Okay, so that's the background. That's a level curve, contour plot, and let's go ahead and try an example here. Sketch the contour plot of f of xy equals x squared minus 4y squared. So, if you don't know what this is going to look like, this is going to be a hyperbolic paraboloid or a Pringle or a horse saddle or whatever you want to call it. So this is going to be one of the more interesting contour plots that we'll draw. Okay, and to get started, we could say, let's let f of xy, or z, right, equal 0. And if I plug 0 into x squared minus 4y squared, we get that 4y squared has to be x squared. In other words, if we've got y alone, we could say y is going to be plus or minus 1/2 x. Right? Move the 4 over, square root it. So I'll kind of do that over here. So do that in different colors. A contour plot is, yes. We're not actually sketching the surface, we're just sketching the level curves, which tells us what's going on the surface without actually having to see it. So 1/2 x negative 1/2 x roughly. And I will label, this was when z was equal to 0, right? So if we're walking on this surface, as long as we stay on this path or that path, we will stay at a height of 0. We're not going to go up, we're not going to go down. Okay, and just to pick some convenient values here, let's say I did z equals 4. So then if I did 4 equals x squared minus 4y squared, divide by 4 to get it into a familiar format. What is this?
A two-phase hyperbola.
It's just a hyperbola,
Oh.
right?
Oh. But if it was a z on the other side, it would be.
The center would be at 0, 0. It opens in what direction here? It opens in the x direction, right? The positive term tells you the direction that it opens in. So let me do that in orange. If you want to do the box thing, we would go, what, 2 and 1? So actually we would get this, right? All right. And let's just get one more. Let's say I did z equals negative 4. So we have z equals 0, z equals 4, and we'll pick one more nice value. If I do negative 4 equals x squared minus 4y squared and divide by negative 4, now we get y squared over 1 minus x squared over 4. So it's the same kind of thing here. The only difference is that this hyperbola opens in the y direction. I'll do that one in green. Oh shoot, I messed that up. Sorry about that. That should be here. Roughly something like that. Ignore that. Okay. So, if I labeled the heights, we have z equals 0. This was z equals negative 4. And the orange was z equals positive 4, right? So, just by looking at that, you could gather some information about what's going on with this shape. For instance, if I start at the origin 0, 0, and I start walking in the positive x direction, what's going to happen to my height? Am I going to climb or am I going to go down? You're going to go up, right? Because that's what the contour plot says. And if I were to go left, same thing. If I were to travel in the positive y or negative y direction, now we'd start to decline. Okay? Yes?
So if you were to take a plane and just slice this hyperbolic graph
Yes.
at x equals 0, all you're going to get is 2 lines.
You mean z equals 0?
Z equals 0, yeah.
Yes, that's exactly what you would get. After I'm done with the lesson, I have some on Maple that I will show you. Yes. And believe it or not, you've actually seen one already. You just didn't know that that's what those were at the time. So, but I'll put it back up. Okay, so that's contour plots. The last thing we need to touch on is a level surface, which is basically the last thing we can do as far as interpreting what's going on. So a three-dimensional object, if I were to take slices and do a two-dimensional representation of that, we get a contour plot. We do level curves. If I have a four-dimensional object and I want to try to think about it in terms of representing that somehow in 3 dimensions, now we get what we call a level surface. Did you have a question?
Yeah. Just for the two hyperbolas, the green one and the orange one.
Yep.
Are there points where are the endpoints supposed to be attached? Is it 2 and 1?
It's two, yes. So for the orange hyperbola, I know it opens in the x direction because
Oh, it's a square root.
yes, and it's 2 away from the origin, yeah. And then same with the lime green one. Opens in the y direction and it's 1 unit away. Okay, so a level surface. Let's recap. 2 variables. Okay. So if we have 2 variables, a function of 2 variables, we get surfaces, and we can interpret that and project that as level curves. If we have a function in 3 variables, okay, this is going to be some 4-dimensional graph that we are not going to do, obviously. But instead of projecting as level curves, we project as a level surface. It's just the natural extension of what we just did. If a 3D graph can be projected 2-dimensionally with a contour plot or a level curve, then a 4-dimensional graph, we can do the same kind of thing, and we get a surface when we dissect it. Okay, so for example, and this is the last problem we'll do, if we have f of x, y, z equals x squared plus y squared plus z squared. And let's say, again, typically we'll say this is the same as w, right? If I did w equals 1, I'm almost off the page, but I'm also almost done, so I'm not going to start a new one. What shape would I get if I plugged 1 into here? A sphere centered at the origin, radius is 1. What if I did w equals, oh, I don't know, 4? I get another sphere, right? So this four-dimensional graph, if we were to project this onto 3 dimensions and try to interpret it like we did with level curves, we get a set of level surfaces which are all spheres, concentric spheres at that. So this would be the first level surface. And then, so this is W equals 1. And then if I went to W equals 4, oh boy, really messed that up. That's okay. So we just get larger and larger spheres as we increase the value for W, or f of x, y, z. Okay? So at this point, you need to be able to sketch all the graphs that we studied in chapter 11. You should be able to sketch some level curves and understand that if you sketch several level curves, we get what we call a contour plot. And then you can interpret the contour plot just like the stuff that you've seen. Yes, if you look at any survey, if you're hiking or whatever, sometimes you can get those maps and they tell you where the different heights are and stuff like that. Yes?
Level curves on the XY plane